The last thing we want to do, take a look at before we leave solutions, is to take a look at how we can use colligative properties like in real life. So yeah, when we're adding salt to a road in winter, it depresses the freezing point. So yeah, that's a way of looking at how this is used in real life. But a way that really combines a lot of this stuff that we've talked about in this chapter in a way that makes sense is to take a look at a process called fractional distillation. If you go on in chemistry and study organic chemistry, you will be doing a lot of these fractional distillations. So let's talk about how this works. So previously, I showed you a curve that had a mixture of, it had two compounds. So we were looking at mole fractions of compounds on the x-axis, y-axis we were looking at pressure. So we saw how to determine the vapor pressure of such a solution of volatile liquids as a function of composition, but we were keeping the temperature constant. Now, since the vapor pressure changes with temperature, what happens if we, instead of looking at composition, what if we look at temperature and pressure? So here, we're looking at the same mixture. We've got benzene, we've got toluene, and then this green line is going to be your mixture. Y-axis, we're looking at pressures measured in millimeters of mercury. X-axis, we're looking at temperature. Okay, so the line, if you notice, the green arrow is pointing to this point right here, because this is going to be 760 millimeters of mercury, and by definition, the temperature at which the pressure is at 760 millimeters of mercury, that's your boiling point. Okay, so this is going to be your boiling point of this mixture. Okay, and so it's actually telling you right here that line is going to be 365.3 Kelvin. Okay, now we can also, at that temperature, if we look at that pressure, if we look at that, if we intersect that line at that pressure, if we go above and below, we can actually see at what pressures do those curves correspond to at a certain temperature. And so that's what we're measuring: the pressure of pure toluene at 365.3 Kelvin, as well as the pressure of pure benzene at 365.3 Kelvin. All right, so what is different about this picture than the others that we've seen? This is a mixture of volatile liquids. All right, and then what equation allows one to calculate this curve? Well, it's going to be something back from the last chapter, chapter 12. This is the Clapeyron equation. All right, so what is the boiling point of pure benzene? So if we were to look at where this graph intersects at 760 millimeters of mercury, the boiling point of pure benzene is going to be around 353 Kelvin, and the boiling point of pure toluene is going to be at 380 Kelvin. Again, all we did was just draw a line, and where this line intersects at that temperature at 760 millimeters of mercury, that's the boiling point. Okay, now the green line corresponds to a 1-to-1 mixture of the two. That boiling point is at 365.3 Kelvin. Now, why is this green line not equidistant from the two? Now, in the previous picture that we looked at, they were, and that was assuming that the temperature is held constant. Here, we can't. All right, so why is the green line not equidistant from the other lines? It's because they're not equal amounts. Okay, so if one collects the vapor above the 1-to-1 mixture, what is its mole fraction of benzene? Well, if we were to calculate the mole fraction of benzene, okay, that would be saying if we got the pressure of the mixture at that pressure divided by the pressure of pure benzene, if we were to calculate the mole fraction, it should be around 0.71. And if one condenses this vapor to a liquid, then heats it to boiling, what is the mole fraction of the benzene in the second? So what this is saying is, if we take that mixture that we collected, okay, that vapor, we condense it back to liquid, okay, and then we heat it up again. And when we heat it up again and we collect that vapor, what should the second vapor do? It should be closer to 1. It's going to be 0.86. So the more times we do this, we collect the vapor, collect the vapor, condense it to liquid, and then heat it up again to it becomes vapor, and then collect that vapor, and then keep repeating this. The more times we keep processing this, so we go from liquid to vapor, back to liquid, back to vapor, back to liquid, back to vapor. The more times we do that, the more pure the mixture becomes, or it's getting closer and closer to a mole fraction of 1. So this process that we're talking about is called fractional distillation. Okay, and so this actually, we got another graph here that actually talks about the phase system diagram between benzene and toluene. So you've got this mixture, okay, you've got them, and you got x-axis, on the y-axis you got temperature, x-axis you've got the mole fractions. Okay, so as you keep increasing the temperature, okay, and you collect that vapor. So what do the horizontal lines mean here? The horizontal lines mean that we've got an equilibrium between the liquid and the gas. And what do the vertical red lines mean? That means it's condensing water or from vapor to liquid. Okay, so the green curve right here is the liquid. The orangey area is the vapor. So every time we've got we're going horizontal, this is going to be an equilibrium between the vapor and the liquid. Every time we go vertical, we're condensing. So if we're going down, we're condensing. If we're going up, we're vaporizing. And so the setup for this, for a fractional distillation, this is pretty much what a column looks like. You're going to be boiling a liquid. The vapor goes up the column to the point where we can record that temperature, and then the vapor will go down this tube, and now we have water rushing through our system where we're going to condense it. We're pushing cold water through, so that way the vapor turns to liquid, and then we collect that liquid down here. Now the goal here, though, is that the more times that we can purify this mixture, more times that we can make it go from liquid to vapor, back to liquid, back to vapor, the more times we can keep doing this, the more pure our collection will be. So that's kind of the plan here. So usually when we do a fractional distillation, we're dealing with two volatile substances and we need to separate them out. So usually the volatile substances, we're dealing with a boiling point around 20 degrees from each other. What we're trying to do is get it separated, so that way we're dealing with usually just one component.